previous lecture we were discussing about like the how to write the basic principle of angular momentum conservation for a control volume, and we will look into some examples related to that, but just to physically appreciate that what kind of examples are there, maybe let us look into one or two cases. We will see that what are the differences in like practical cases when you have a linear momentum and angular momentum conservation. So, first we will look into an example which we discussed it in some way, that basically you have a flat object on which there is water which is falling, and you can see that the reality is so different from what we considered. The water jet may not be thin, the water jet may be having different thicknesses at different sections. So, it is a gross simplification of what we could see. Now, think about look into a situation when the water jet is falling on something which is mounted on with respect to one axis, and when it is doing like that, it creates a moment of the linear momentum or the angular momentum, and that mounted wheel starts rotating, and that is the basic principle of a turbine that we will see later on when we will be discussing about the hydraulic machines. But now before going into such complicated things of fluid machines, see this example. This also gives a very important example of angular momentum conservation. This is a lawn sprinkler. So, this is commonly used for watering the gardens, and if you see that water is coming out of the limbs of the sprinkler, and when water is coming out, that water comes out with a velocity because water is supplied at a given velocity, and when water is coming out with that velocity, what is happening? Basically it is having a linear momentum. That linear momentum has a moment with respect to the axis of the sprinkler. So, there is an angular momentum, and there is a rate of change of angular momentum that makes it rotate. Even if it is if there is no frictional resistance, that will make it rotate very fast. Because of some frictional resistance against rotation in the pivot which is there, it will not rotate as easily as we might think, but still you have seen in this example that it might rotate quite easily. So, if you see initially there is no rotation, but when the water is coming out, see we are trying to develop an understanding that it is actually an unsteady problem. So, that is the first thing to appreciate. It is not a steady problem, because you see that the entire physical behavior what we are observing here is a function of time, and our important objective will be to see that if it develops an angular velocity from say time equal to 0 to some time equal to t, then how that angular velocity evolves with time. So, this lawn sprinkler example is a very simple example, but it can demonstrate a good use of the angular momentum conservation principle, and this principle in a more elaborate way is used for analyzing those fluid machines which are basically of rotating nature. Like there are two very common devices which we will be discussing later on. One is a centrifugal pump and another is a rotating turbine. So, we will be discussing about these things in more details. That will probably be our last chapter in this course of fluid mechanics, that is the fundamentals of fluid machines. Right now we will not go into that application, but we will concentrate more on a simple example. So, we will use this for a case. So, let us take that example. So, when we consider that example, we will simplify whatever thing which we saw in the practicality. We will consider that there is only one limb like this of the sprinkler, and this entire thing is in a horizontal plane, rotating in a horizontal plane. Just think that it is one arm. There could be many such arms, but we are just concentrating on one arm. So, the water is moving at a uniform velocity relative to the rotating arm. So, the arm is rotating. If you had looked into the examples very carefully, no matter wherever the arms are there, the water relative to the arm is was coming out with a fixed velocity, because that is the rate at which it is being provided. So, the water it comes to the center and then gets distributed along the arm, moves along the arm with a uniform or a constant velocity relative to the arm, and eventually it goes out like what shown in the figure. And let us say that it starts rotating with an angular velocity omega, which itself may be a function of time, and our objective is to find out what is this omega as a function of time. Let us say that we know that rho is the density of the water and q is the total rate of supply of water, volume flow rate. So, this is volume flow rate like meter cube per second. Okay. So, we will try to analyze this problem in two ways. One is with an inertial reference frame, another is with a moving reference frame, and we will try to see whether we converge to the same conclusion or not. We start with the moving reference frame, that is we as if we attach the reference frame with the sprinkler arm, which is rotating with a given angular velocity, with not a given, with some angular velocity which is a function of time, and therefore it is subjected also to some angular acceleration, but it is not translating. So, now we are having a control volume which is a rotating control volume, but not a translating one. See, this problem is a symmetric problem with respect to the center of the arm. So, we may take say a control volume, say half of the entire thing. When you have a problem which has symmetry in certain ways and the physics is also symmetrical, geometry is also symmetrical, then you can reduce your task or burden by taking a symmetrical part of the problem. So, we have taken one symmetrical half of the problem. In this problem we have neglected one thing, we have assumed that the vertical part of the limb is very small. So, it is mainly a horizontal one and the vertical is very small. Remember that this is actually in a horizontal plane. So, just because we have to draw it in the plane of the board, it appears to be like it is upwards, but it is like in a plane it is a bit bent like that, and that bent part is quite small that we are assuming. It is just to give it a sufficient change in direction, but not enough length. That is what is the assumption, and let us say that the radius is capital R, which is the radius of each limb, and that is symmetric. So, we will write first the equation for the moving reference frame. So, when we write the equation for the moving reference frame, we will use this form whatever we discussed in the previous class. One important correction which one of your friends has mentioned, and it is quite correct, that this term is not going to be there in the A relative expression, because this like when we wrote A relative, that was basically A capital XY z minus A small xyz, and that is how this actually got nullified in that expression. So, we need not duplicate it. So, this term is not there in the A relative one, just keep in mind that was a mistake and you please correct that. Now, next is so let us try to apply this one with respect to this expression. So, the resultant again we are considering that it is a frictionless pivot. So, what it tells is that there is no frictional resistance moment when this is rotating. So, this is rotating like freely, so to say. So, when this is rotating freely, you have the resultant moment of all external forces because of what? One may be because of the frictional torque which is present. So, frictional torque we are assuming to be 0, but there could be torque because of the weight distribution, and because it is symmetrically distributed, the resultant torque due to weight it is there or not there. So, let us consider a small element in the, so you have a symmetrically located thing, a small element in this side will always be counterbalanced by an equivalent small element in the other side in terms of the rotational thing. So, there is actually no resultant moment of external forces, because only two external forces could be that rotational resistance plus the moment of the distributed weight. Okay. So, that is not there. So, that is a null vector. Then let us, if you consider the moving reference frame, so in the moving reference frame we have this correction term. So, A relative. So, in the A relative first term is acceleration of the control volume, that is the linear acceleration of the control volume, here that is 0. Next are the 3 rotational terms that we need to consider. So, what are the rotational terms? 2 omega cross V small xyz. So, V small xyz is what? It is the velocity of the fluid relative to the control volume. We are assuming that it is moving at a constant velocity relative to the control volume. So, V small xyz is like a constant, but if you want to write this term properly, let us write minus integral of r cross A relative into dm for the control volume. So, what we will do, we will let us say we will split this A relative into different parts instead of just writing it in a cumbersome single expression. So, we will find out the contribution of the 3 different terms which are there. So, so before doing that, what is this dm, that you have to keep in mind. Dm is some small element at a distance, at a radial distance of small r. You can take a strip of width dr, and let us say that capital A is the area of cross section of the sprinkler, this area of cross section. So, dm is what? If dm is the elemental mass of the shaded volume, then what is that? dm is rho A dr, right. So, basically when you are writing the expression, this will be integral of whatever you write as A relative with this entire thing, that multiplied by rho r dr, integrated from small r equal to 0 to small r equal to capital R. That will be the that correction term in the left hand side. So, before applying that correction term, let us write these things in a vector form. So, what is omega in a vector form? Let us say this is xy plane, yes, omega k. What is V small xyz? No, this is by positive sign convention. If it comes out to be minus something, then that will be like that. So, then what is V small xyz? So, it is moving, no, V small xyz is what? Velocity of the water relative to the sprinkler. So, say it is moving at a velocity V r relative to the sprinkler in a magnitude sense, vector sense, yes, with these 2 options I or j, yes, only 2 options are there, it cannot be k. So, only I and j, yes, I or j. You are not very sure it should be I. See, when you are considering this will be a volume integral, this part is negligible in comparison to this part. So, it should be ideally for this part I and for this part j, but because I have already mentioned that this is like of negligible length, in the volume integral only this horizontal part is mattering, and there it is moving radially. So, it is like V r I, okay. Then omega dot, that is the only other thing that is remaining. Let us say that is omega dot k. Let us say omega dot also has a positive sense like that. So, A relative, first 2 omega cross V small x y z. So, these two cross product. So, 2 omega V r j, then omega cross r. What is omega cross r? What is r in a vector form? Ri. So, omega cross r is omega r j, and omega cross r is minus omega square r I. So, it is just like centripetal acceleration. So, minus omega square r I, then next is omega dot r j. Now, if you make r cross A relative, so you will clearly see that the centripetal term will not be there because it is directed along r. So, its moment will be 0, but other terms will be there. So, 2 omega V r k plus omega dot r k with r multiplied, right. So, let us write r square. So, when you write this particular term, now we are in a position to write it in a proper integral form. So, that will be minus of 2 omega V r plus omega dot r square into r dA, sorry, rho A dr, that is dV, zero to capital R, right. So, that will become minus rho A omega V r capital R square plus omega dot r cube by 3. Okay. Then the right hand side, let us write the right hand side. Right hand side, now you tell, the left hand side we have completed, right hand side what will be the first term? You have to see what are the things which are functions of time. V small x y z is not a function of time, because we are assuming that relative to the sprinkler arm the water is moving at a constant velocity. So, no matter how the arm is moving, but relative to that, and we are writing it only relative to that, it is not changing with time, neither the volume of the control volume is changing with time. So, this term will be 0. So, in the right hand side the first term will be 0, and what will be the second term? Second term is the flow boundary, it represents what happens at the flow boundary. So, for the second term when you substitute that, so let us assume that these velocities are again uniformly distributed over the flow boundary. So, V dot eta dA, this term if you just keep it inside, now r cross V small x y z, can you take it to be independent of the area and bring it out of the integral? Yes or no? What is this r now? These are where? This is some r located at the flow boundary, that means at these locations somewhere. Because this is very thin, it does not really matter exactly that where is the variation, but it is somewhere here. So, that is basically capital R I plus something j plus some little something j, that is the radius outside. So, let us say that it is capital R, let us give it a name, say A, keeping in mind that A is small. So, R I plus A j, that is R cross V small x y z is a constant. So, that also we can take it out of the integral, provided with also consider it to be constant over the area, uniform over the area. So, if you assume it to be uniform over the area, we just take it out and that is V relative, and then rho is there, of course rho let us write. The remaining thing which is there in the integral is the volume flow rate over that section. So, what is the volume flow rate over that section? Yes, it is q by 2. See, we have only taken the half of this, that half of the q flows through this, half of the q flows through this, there is no exception because it is perfectly symmetrical. So, this into q by 2, that is the right hand side, and the question is what will you put this in a vector form. So, Vr what, I or j, this one Vr j, right. So, you will see that this little part A will not matter because of the cross product. So, it will become, let us write it completely, it is equal to rho Vr R q by 2 k. Since the left hand side is equal to the right hand side, so the left hand side equal to the right hand side, which implies what? Minus rho A omega Vr R square plus omega dot R cube by 3 is equal to rho Vr R q by 2. This we missed that k cap, the vector sign that was there. So, this omega dot is nothing but d omega dt. Vr you know, because what is Vr? Vr is the flow rate divided by the area. So, q by 2 divided by A. So, given the flow rate, you should be in a position to substitute Vr, which is a constant. So, only the variables are d omega dt and omega. So, it is a differential equation of the form something into d omega dt plus something into omega is some constant, right. So, it is you may separate the variables easily to solve it, because these are constant coefficients here. Now, let us try to look into the problem from an inertial reference viewpoint and see that whether we can solve the same problem in that way. So, now we will get rid of the non inertial corrections and we will just consider that we are looking for control volume, which is maybe schematically you draw it like this, but that is not moving with the arm. So, even if the arm goes to a different place, the control volume is fixed. So, at that instant we are trying to we are considering one particular instant when the control volume and the arm they are coinciding, and at that instant we are trying to figure out what is happening. Now, if you consider the inertial problem, that is the inertial reference frame way of looking into it, the left hand side is 0, right. the left hand side is 0 or null vector, the right hand side. Now you see that with respect to an inertial reference frame it will be unsteady, right. If it was moving at a constant velocity relative to the reference frame, then sitting on the reference frame you look it as a constant, but standing from outside which is inertial you see that velocity is changing with time, because the frame velocity itself is changing with time. So this time derivative term with respect to an inertial frame will not go to 0. So the right hand side, therefore you have to write this time derivative term properly. So when you write it then let us write r, again r you write as r I cap, because the volume which is involved for the control volume integral, this is the control volume integral. So their major part is the horizontal part. Then what is this V? What is this V? This is velocity of the solid plus velocity of the fluid relative to the solid. So what is the velocity of the solid at the coincident point at a radial location r? It is omega cross r. So this is the velocity of the solid plus the velocity of the fluid or V relative or Vr. So this is omega rj plus Vri, right. So we substitute that, but before substituting maybe it is useful to find out what is r cross V. So that is omega r square k. Then so you write this as omega r square, then in place of dV a dr, this thing k, right, then plus again you assume uniform velocity distribution. So when you write the next term, then what should you substitute for this V? This one, yes. Remember this V has to be inertial reference frame V. So what is that? So omega k cross with capital R I plus A j plus V R j, right. So what will be that? Omega r j plus omega a minus I plus V r j. So if you make another r cross with that, then what is that r? That r is again this capital R I plus A j. So what is that r cross? Cross with that one, omega r j minus omega a I plus B r j, right. So here if you neglect small a, then like that is what is given in the statement of the problem. So, just neglect the small a part. So, it is omega r plus Vr into capital R k. So, the next term we will write. Yes.
Where do we get that Vr k cap from? We have calculated omega cross r, right?
This is omega cross r is what? So, if you consider a point here, the point first, how do you consider a coincident point in the solid plus velocity of the fluid relative to that coincident point, okay, that is the absolute velocity of the fluid. Vr is V relative, yes. So, the same Vr that we used in the even the previous method. So, the next term is omega r square then integral of rho Vr dot eta dA over the control surface with a k cap. So, now what we do, we simplify the different terms just like what we did in the previous case or in the previous method. Rho is a constant that we are considering for this problem. So, we are taking that rho here out of the left hand side and right hand side. So, left hand side equal to right hand side when we write. So, 0 equal to, now you see first of all we integrate with respect to position. So, when you integrate with respect to position, it is from 0 to capital R. So, you have basically first let us complete the integral. So, integral will be rho a omega capital R cube by 3. Now, a partial derivative of that with respect to time, and then the remaining one plus omega r square into rho into the remaining term is q by 2, because remember no matter whether it is inertial or non inertial, this velocity is always V relative for flow rate part calculation, okay. Now, rho being constant, a being constant, r being constant, but omega is not a constant. So, you have rho a omega maybe by divided by 3 also, sorry, rho a r cube by 3, then you have d omega dt plus now there has been a point where I have omitted one term. Where is that term? This is your work to identify. You may get a clue by comparing with the previous method and this method, they should at the end give the same result no matter what is the control volume. So, some term is omitted somewhere. Which term? Vr into, where is that term? R cross V. So, what is there? Plus rho, you tell, I will just write R into Vr into q by 2. So, one term because of multiplication of this with R, because of this with R, that was omitted, I mean not omitted, just somehow not written here. So, So, that is equal to 0, and this should give the same differential equation as what we obtained with a non inertial reference frame. It should not be fundamentally different. Okay. So, what we have understood is that you may use different reference frames, but when you go to your final analysis, the final analysis should converge to the same conclusion. Now, what you may do, a little bit of modification of this, that when you take the part small a not very small, that is it is of substantial length, then neglecting it and not neglecting it will matter more for approach 1 or approach 2, that is will matter more for the inertial frame based analysis or non inertial frame based analysis. That is a bit of more thing that you can add with this one, but again the principle will be very similar. Then you do not neglect the terms with small a and just do the algebra, and then you will easily find it out. Now, what we have seen here, so in this particular chapter, what we have discussed in this particular chapter, we have found out how, or we have learnt how to write the integral forms of conservation equations for mass conservation, linear momentum conservation and angular momentum conservation. In one case, we have at least shown that you may convert the integral form to a differential form, and that is the mass conservation example which gave back the continuity equation. So, what was the differential form? Let us write it once more. This was the differential form that we derived. We should keep in mind that this here everything is written in the index notation. That means there are certain terms where there is an invisible summation. In which term there are summations? There are 2 terms in the left hand side and 2 terms in the right hand side. So, out of these terms, in which terms you have summations? Second term in the left hand side, because you have this repeated index, right. So, this is actually summation of this one with j running from 1 to 3. That means wherever there is such a repeated index, this is like a dummy index. In place of j you could write k, l, m, whatever, because that is not the index that is like free for you. I mean it is summed up. Here also it is j equal to 1 to 3, because it is a repeated index. So, whatever index is not a repeated index, here I is not a repeated index. So, I you are free to choose. So, I equal to 1 will give the x component of the momentum conservation equation, I equal to 2 will give the y component, I equal to 3 will give the z component. That is the basic way of looking into it. So, it is also possible therefore to write in a way in which you write the velocity components u v w. So, alternative notations, if you write in terms of u v w, you write, let us say you write I equal to 1. So, it is u1 which is equivalent to u, the x component of the velocity. So, what is this? Then such a summation. So, this is the equation written for motion along x. You see the advantage with the index notation is so compact, and this when you have expanded it, it does not look that compact. Obviously it means the same. Whenever we will be looking for analytical solutions, we will be expanding in this form, but at the same time for the convenience of writing and understanding, the index notation many times is quite suitable. Now we will start with this equation, we will use the index notation for deriving the rest of the things, but whatever is our final form, again we will come back to the alternative notation, so that you may use those forms for solving the problems. Now we will start with this form with a question, what are the assumptions under which this is valid, because we may proceed only from that. So we need to understand that what are the assumptions which are inbuilt with this equation. What kind of assumptions were there? Well, continuum, yes, because these are continuum conservation equations. Any more assumption? The reference frame is stationary, that was the assumption, right. So if you have a moving reference frame, it would be easy and straightforward to derive the form, because if you recall how did these terms appear. So you had a resultant force in the left hand side of the statement of the Reynolds transport theorem, there you had surface forces and body forces, this term came from surface forces, this term came from body forces, and in the right hand side there was a transient term from which this came, and there was an advection term because of the transport of the fluid across the surface of the control volume, from that this term came by converting it into a volume integral. So it is important to keep in mind that what these are. We will see later on that it is equivalent to an equation written in an Eulerian description, where the left hand side is like acceleration per unit mass say, and right hand side is force per unit mass. So it is as good as like almost like Newton's second law of motion. Now the other question is that at which we partially address, that what are the physical significances of these terms, and if you look for these terms, we will recognize that this right hand side we had recognized, the left hand side we will see that it will come as some function of acceleration, or it will be directly related to the acceleration. So acceleration of the flow is related somehow with the transience, that is the unsteady effect that is at a particular location if things change with time, and if there is a change because of the change in position from one point to another point where the particle finds a new flow field, that is the advective effect, and the combination of that is the total derivative. We will be able to express this in terms of the total derivative, that we will do subsequently. If you want to write this for a non-inertial reference frame, you have to just keep in mind that the left hand side for a non-inertial reference frame is corrected with a correction factor minus equivalent to like a D'Alembert's force, like minus mass into acceleration, that type of term, where that is like a relative acceleration. In that relative acceleration you have terms related to the angular velocity of the reference frame or angular acceleration of the reference frame, like that. So you can incorporate those correction terms, and that is itself a volume integral, and derive it in the same way. You will see that you will get some extra terms because of the transformation of coordinates. Otherwise this is quite straightforward, and the advantage or the like the elegance of this form is that it is independent of the nature of the fluid that you are looking for. Till now we have not committed ourselves to whether the fluid is Newtonian, non-Newtonian or whatever, it is just for any generic fluid. So this equation is known as Navier's equation of equilibrium. This much we discussed in the last class, but this is just a brief recapitulation so that we may start with this. Now our objective will be to see that what equations we have with us. See, what is our objective? Our objective is to have sufficient equations so that we may solve for the unknown variables. So we have to identify what are the unknown variables. See, if you look into this equation, what would be the unknowns? See, definitely if you have a forcing on a system, you know what is the body force, because if you do not know what is the force to which it is subjected, you cannot find out how the system evolves under the action of the force. So, you know the force. What are the things which are unknown here? The velocity components are unknown here, and also the stress tensor components, these are not known to you. So, the stress tensor components in turn may be expressed in terms of the velocities, and that we have to see that is it in terms of the velocities directly or in terms of the gradients of velocities. So, we can qualitatively understand from our studies in kinematics of flows that any deformation for a fluid is actually the not important in an absolute sense, but the rate of deformation is what is important in an absolute sense. So, when we say rate of deformation, we mean linear deformation, angular deformation. Linear deformation may give rise to a volumetric change. So, all these are expressed in terms of rates for fluids, because the understanding is fluids are anyway continuously deforming. So, if we allow more and more time, deformation will be more and more, that is not a quantification of anything. Quantification is the rate at which that deformation is taking place, or the rate of strain, so to say. Now, that rate of strain should be related to this one, but we have to keep in mind that there is a forcing condition, there is a surface forcing condition which should not depend on the rate of deformation. What is that surface forcing condition? So, if you have a force on a surface, see this somehow is a representative of what is the forcing condition on a surface of a fluid element. Now, there is a part of that forcing condition which should not be dependent on the rate of deformation, and that we should isolate. What is that? That should be the pressure distribution, because we have seen that what is the hallmark of a fluid at rest. If there is a fluid at rest, that means it is not deforming, and we know that fluids are in continuous deformation subjected to shear forces. So, that means when fluid is at rest, there are two important things which are occurring. One is there is no shear force, because if there is a shear force, it will start deforming, except for some special fluids which we have discussed as some special non-Newtonian fluids, but in general if you apply a force, the fluid will start its deformation. So, if it is at rest, that means there is no shear force, there is only normal force, but a special type of normal force that is not dependent on its deformation, because you can also have a normal force which may be related to deformation, may not be angular deformation, but may be volumetric deformation. So, if you have an element, you may be able to stretch it or compress it by a normal force. So, it is not just true that if you have a normal force, then that is not related to deformation. Normal force also may be related to deformation, but pressure is going to be such a normal force which is not related to the deformation, because it is equally applicable for fluids at rest which are not under deformation. That does not mean that when a fluid is moving, it does not have pressure. Simply we can isolate that effect and say that whatever is the remaining effect, that is related to the deformation of the fluid. So, when a fluid is moving, it is equally subjected to pressure, but we may isolate that part and say yes, the effect due to pressure was something which was not responsible for its deformation, and anything else would be responsible for its deformation. Accordingly, what we may do is we may decompose this tau ij into two parts. One part we say is a hydrostatic component, and the other part we call as a deviatory component. So, hydrostatic component is something, from the name it is clear that as if it talks about a static condition. So, it is not related to therefore deformation. So, we can broadly say that we are decomposing it into two components. One component is not related to deformation, another component is related to deformation. That is the whole idea. And when the component that is related to deformation, that component should be only a function of pressure, because when a fluid is at rest, you can only have the description of the equilibrium through the pressure.